Hi everybody, this is Dr. Bricker here with a Homework 5 help video. So Homework 5 deals with Chapter 9, which is the Momentum and Impulse chapter. Here's the first problem. A student throws a 110-gram snowball at 8.5 meters per second at the side of the schoolhouse, where it hits and sticks. What is the magnitude of the average force on the wall if the duration of the collision is 0.16 seconds? Okay, let's take a look at this impulse relationship idea. Okay, here's the mass. I converted it to kilograms divided by 1,000. The initial speed is 8.5, and the collision takes 0.16 seconds. Another thing to note here is that the snowball comes to rest, so the final speed of the snowball is 0. Now, if you want to, you could do this without using the impulse relationship. From the initial and final speed and the time, you could figure out the acceleration, and then the average force here would be the acceleration times the mass from Newton's second law. Luckily, we have this impulse relationship that will make our lives a little bit easier, hopefully. So impulse, J is a symbol for impulse. It's just another word for change in momentum. Okay, so it is related to the force, but it's not like it has to be a quick force. It means change in momentum. The word impulse makes you think that it's just some kind of short duration force, and it doesn't have to be. So this is equal to force times time. So that's the change in momentum. Final momentum minus initial momentum. MV final minus MV initial. Lots of different ways of writing it. So whenever you have a problem that involves force, time, mass, and velocity, think about the impulse relationship. Okay, this is also the equation that could save your life. So let me write it over here. F times time is the change in momentum. So if you divide both sides by the amount of time, you get the force. So say you get into a car accident and you're going to have a certain amount of change in momentum. Regardless, if you go from 60 to 0, you have a mass, you're going to have a change in momentum. The larger the time of the collision, so if you can make t bigger, you make the average force smaller. That's the idea between crumple zones, airbags. You're trying to make the t larger to make the average force smaller. Probably when we were talking about Newton's laws, you were thinking there should be a time component involved with the force, and there is, and it comes about in this impulse relationship that you see here. Okay, people have survived parachutes not opening by, regardless, having the same change in momentum, making the time larger, you can make the average force smaller. Okay, so back to this problem. We're given mass, velocities, time, and we're looking for force. It's a perfect candidate for the impulse relationship. And actually, I have it written nicely here, what the form that we could use. So force is mv final minus mv initial divided by the amount of time. And the final speed is 0. This will come out to be negative because the force is the opposite direction that you're moving. The question just wants you to give the magnitude of the force. Okay, so from this you can get the actual force, absolute value of that, to get the magnitude. Let's look at the next one. Okay, so here in this picture we have a force versus time graph. So you can see the force changes up to a maximum amount, comes back down to 0. So force here on the vertical axis, time in milliseconds on the horizontal axis. Let's see, in the figure, the value of F max gives an impulse of 6 Newton seconds. Express your answer in newtons to 2 figures. Oh, sorry. In the figure, what value of F max gives an impulse of 6 newtons times seconds? Okay, so if you have a graph of force versus time, the impulse turns out to be the area under the curve. So whatever this area is, that's what the impulse is. Let's take a look at this and solve this one. Okay, so time, 8 milliseconds, or 8 times 10 to the minus third. That's the base of that triangle. We're trying to figure out the maximum force, and they give you the impulse. They give you the area under the curve. Okay, so the area of a triangle is 1/2 the base, so the base is the time. The height is F max. So that's the area of a triangle. And then this is equal to the impulse. Okay, and then you know everything except for what you're looking for. You're trying to figure out this. So multiply both sides by 2, divide by the amount of time. So 2 times j divided by the amount of time. And then just be careful. Remember, this is milliseconds. Okay. All right, let's look at the next one. Okay, next one. In a Little League baseball game, a 145 gram, okay, perfectly good. Just remember, you got to put that in the kilograms, enters the strike zone with a speed of 15. The batter hits the ball. It leaves his bat with a speed of 22 in exactly the opposite direction. What is the magnitude of the impulse? And then next part here, if the bat is in contact with the ball for 1.3 milliseconds, what's the average force? Okay, so we have to be careful. If the ball comes in at 15 meters per second one direction, goes back at 22 in the other direction, impulse is a vector quantity. If we say 15 is positive, 22's got to be negative. You have to bring that to the problem. Okay, let's take a look at this one. Okay, so initial speed is 15, and if I'm saying that's positive, that's got to be negative. Mass is 0.145. We want the magnitude of the impulse. So you saw the formula earlier. Impulse is the change in momentum. I mean, it's also equal to force times time, all the other parts, but this is the only part of this that we actually need. mv final minus mv initial. So if you want, you could factor out a m actually. So we've got the mass, 0.145 kilograms. V final, don't forget the minus sign. And then minus 15. Let's see what we get for this. This is going to come out to be negative, but the question's just asking for the magnitude. Okay, so we've got 0.145 times the quantity, negative 22 minus 15. Okay, so negative 5.365 kilogram meters per second. Okay, so that's the actual impulse. The way I've set this up, we just want the absolute value of that for the first question. Okay, and then to figure out the amount of time, actually with this one, we are given the amount of time, and we have to get the force. Sorry about that. So time was given. How much force does the bat impart to the ball? Okay, so same thing. F times time, the magnitude of that is equal to the impulse, which you just found. So then the average force would be the impulse divided by the amount of time. I called it delta T. I should probably call it delta T here. Same thing. So you have this from the first part, the magnitude of it, the time is given, you can get the average force. So a Newton second, if you look at this, impulse, force times time. This would be Newton times seconds. But we just found up here that impulse is kilogram meter per second. Those are the same thing. Newton second is the same thing as a kilogram meter per second. Well, how could that be? A Newton is a kilogram meter per second squared. So that's a Newton. Multiply it by a second. The seconds cancel out and you get kilogram meter per second. So same thing. Kilogram meter per second and Newton second, same exact thing. Okay, let's look at the next one. Okay, the next one is we have a small cart, 300 grams, moving at 1.9 meters per second on a frictionless track, collides with a larger 1 kilogram cart initially at rest. After the collision, the carts recoil at 0.85. The small cart recoils. Okay, so this is a collision problem. What we've done so far were force, mass, velocity, and time problems. That's one sort of problem in this chapter. Now, if there is no outside force, there's only internal forces, which is what happens with collisions, we can still use the impulse relationship. It's just that the force is zero. There is no change in momentum. So what I'm trying to say is there's two kinds of problems: force, time, mass, and velocity, and then there's collision problems. So those two different categories of problems. So whenever you see a collision problem, we will use the conservation of momentum idea to solve those. So let's take a look at this, and I'll say a little bit more about that. Okay, so what I was saying before, here's the impulse relationship. Force times time, final momentum minus initial momentum. But if the outside force is equal to 0, which it would be with the collision, they're just internal forces, this is equal to 0 then. That's if the outside force is equal to 0. We have this. So if the outside force is equal to 0, the final momentum is equal to the initial momentum. This is the other kind of problem in this chapter, the final momentum being equal to the initial momentum. The other kind of problem is you have an outside force acting with a certain amount of time. You can figure out the impulse, change in momentum that way. Okay, so again, this is the other category of problems. Here's the picture we have at this specific one. Initial velocity of the smaller cart, 1.9 meters per second. Here's the mass. Hits a stationary cart, so this is the initial situation. After the collision, mass 1 recoils to the left at 0.85 meters per second. So it's going the other direction. You've got to put the negative sign there. We want to know how fast this one's moving to the right. So again, the initial momentum in this picture is equal to the final momentum. And we have to calculate that from this picture. Okay? And remember, it's a vector quantity, so that's why this is negative here. That's positive there. Okay, so the initial momentum of the system, mass 1, velocity 1, initial. Mass 2 is not moving, so I'm not even going to write down its momentum. Right? I could do mass 2, velocity 2, initial, but velocity 2 initial is 0, so I'm not going to do that. The final momentum, we have mass 1, velocity 1, final, plus mass 2, velocity 2, final. Okay, so the only thing that you don't know is the thing that you're looking for, velocity 2, final. You'll have to do some algebra here. Mass 1, velocity 1, initial, minus mass 1, velocity 1, final. Make sure that you keep the signs correct there. So I've put that over to the left-hand side. Now divide by mass 2 to get velocity 2, final. And it's got to come out to be positive from this picture. Okay, so be careful with your with the negative signs, and just go through it systematically. Whenever you see a collision, though, this is what you're going to be using. Okay, on to the next one. Okay, in this one we've got a 60-kilogram hunter stands on frictionless ice, shoots a 42-gram bullet. Okay, be careful with that. Horizontally at 640 meters per second. What is the recoil speed of the hunter? Okay, so if you think about it, the hunter shoots the bullet. The bullet goes one way. The hunter's going to have to recoil the other way. There was no momentum to begin with. The hunter and the bullet were stationary. After the sort of collision, after the hunter fires the bullet, we're going to have the bullet go one way. The hunter's going to have to go the other way. Now, as far as the system goes between the hunter and the bullet, afterwards there's no momentum. The bullet has momentum one way, the hunter has momentum back the other way. They're opposites of each other. The net momentum is still 0, just like it was when we began. Okay, let's take a look at this. Okay, it's a little bit brighter. My battery was going dead, I think was the problem. Okay, so before the collision there's no momentum. After the hunter fires the bullet, here's the momentum of the bullet, here's the momentum of the hunter. They're equal to each other. So we still don't have any momentum afterwards of the system. Okay? Now in terms of the momentum of the bullet, we've got the mass of the bullet times the velocity of the bullet one direction. This has got to be equal to the mass of the hunter times the velocity of the hunter the other direction. Now the bullet's going fast, but it doesn't have a lot of mass. The hunter's got a lot more mass, so it's going to be going a lot slower. And you can figure out the recoil speed of the hunter by just doing a little bit of algebra here. And then divide by mass of hunter. Okay, just be careful with the units again. Make sure that if this is in kilograms, this is in kilograms. Okay, very good. It's going to be a small number. All right, let's look at the next one. Okay, 2.7 kilogram block slides along frictionless surface at 1.5. A second block, sliding faster, collides with the first block from behind and sticks to it. Okay, this is something called a perfectly inelastic collision. That just means sticks together. The final velocity of the combined blocks is 2.7. what is the mass of the second block? Okay, we'll have to just set this up systematically. Again, this is a collision problem, so we'll use conservation of momentum whenever you see a collision. All right, let's take a look at this. Okay, so here's mass 2 going faster. It catches up to mass 1. This is before the collision. We know the mass 1 is 2.7. We know how fast it's going. Afterwards, they stick together, and when they stick together, they have a common speed. And again, we know mass 1. We don't know mass 2. So the idea is, the concept is, the initial momentum of the system is equal to the final momentum of the system. Now, the initial momentum in this problem is mass 1 plus velocity 1 initial, because it's actually moving. Same thing with this one, mass 2, velocity 2 initial. And then the final momentum, while they're stuck together, mass 1 plus mass 2 times their final common speed. And then the only thing that you do not know in this algebraic expression is mass 2. You'll have to do some algebra. Let me do one more step. Mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, is mass 1 times that speed, this common speed v, plus mass 2 times v. I'll put dot, 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 get everything with mass 2 on one side of the equation. You have mass 2 is equal to something over here. And then you can solve for it. I would wait to the end to put numbers in. You don't want to write 2.7 and then have to keep write 2.7, 2.7, for mass 1 every different step. I would wait till you get to the end and then put the numbers in. It's a lot easier to accidentally write something other than 2.7. Maybe you mix it up and do 7.2. I'm not accidentally going to write a W instead of a V. That doesn't happen. So it's good to wait, I think, until the end to put the numbers in. A couple steps more of algebra and you should be good. Let's look at the next one. Okay, so in this one you have a 300-gram bird flying at 6.3, sees an insect straight ahead traveling towards it with a speed of 29, okay, as measured by somebody on the ground. Okay, so it's not a relative velocity thing. The bird opens its mouth wide and enjoys a nice lunch. What is the bird's speed immediately after swallowing? Okay, so you can set this one up just like you did the previous problem. Now, in the previous problem, they were both going in the same direction. Here, they're not. The bird is flying, maybe pretend the bird is flying to the right at 6.3. The insect is traveling towards the bird at 29. So that 29 is going to have to be negative. But you set it up the same exact way. The initial momentum of the system, which would be like mass of bird, velocity bird initial, plus mass insect plus velocity insect initial, taking into account that the speed of the insect is negative, would be equal to their total mass, mass of bird plus mass of insect, that quantity times their final common speed. And then what you're trying to figure out is their final common speed. So it's just like the previous problem, the only difference being the insect is going towards the bird. You set it up the same way, and you're solving for something different. You're solving for their common final speed here. It's actually a little bit easier algebraically, I should say, to solve this one. Okay, so you would anticipate that the bird's going to slow down a bit. Not a whole bunch, because the insect is not very massive compared to the bird, although it is going faster. Okay, next one. A kid at a junior high cafeteria wants to propel an empty milk carton along a lunch table by hitting it with a 3.1 gram spitball. Okay, just be careful, that's in grams. If he wants the speed of the 20 gram carton after the spitball hits it to be 0.3, at what speed should his 3.1 spitball hit the carton? And assume the carton and the spitball stick together. Okay, so this is just like what we did before, but let's put this one on paper and take a look at it. But it is completely inelastic collision, meaning they stick together, just like the previous problems. Let's take a look at it. Okay, so mass of the spitball was given, mass of the carton is given. The kid wants the combined speed of the spitball and the carton afterwards to be 0.3. That's here. How fast do you have to spit the spitball? I guess that's what's happening, maybe through a straw or something like that. Here, to stick to the carton, and we're assuming that the carton is not moving initially, it's just stationary. And we're assuming there's no friction on the ground or anything like that. Okay, so it's the same idea. The initial momentum of the system is equal to the final momentum of the system. Now the initial momentum is only contained in the spitball. I could write mass of carton, velocity of carton initial, but I know that's 0, so I'm saving myself a little bit of writing by not doing that. And then afterwards, they're stuck together, common final mass, spitball plus carton, and then common final speed. And then the only thing that you don't know is this. You have to do just one step of algebra to figure out how fast the spitball has to go. Okay, so the spitball is not, 1/7 or something like that, 1/6 or so, the mass of the carton. So it's going to have to go really, really fast to get this to happen. You'll have to solve it to see. Now, if you notice, I left this in grams and this in grams. In this problem, if you're careful with the units, you don't always have to change it to kilograms. This will be in grams if I leave it like this. This is in grams. The grams actually cancel out. You never hurt yourself by converting it to kilograms. The kilograms will cancel out. But I happened to notice that the grams would also cancel out. Okay, let's take a look at the next one. Okay, we've got a 20-gram ball of clay traveling east at 2 meters per second collides with a 30-gram ball of clay traveling 30 degrees south of west. What is the speed of the 50-gram blob of clay? So we're assuming they stick together, and this is a two-dimensional collision. It just takes more work. It's the same exact idea that we had before. And then what is the direction of the 50-gram blob of clay afterwards? Okay, so we'll have to figure out the speed of the clay afterwards in the x direction, the speed of the clay afterwards in the y direction, and then we can get the overall speed of the blob of clay afterwards. And if we know the x velocity afterwards and the y velocity afterwards, you can figure out the direction that it's traveling. Okay, so this is it's not really harder than what we've done. It's just there's more to it because we've got to do x direction and y direction, so there's like twice as much work. But it's not harder per se. It just takes longer. All right, let's set this one up. Okay, so here's the 20-gram clay traveling just east. Here's the 30-gram clay traveling 30 degrees south of west. So it's traveling this way. This blob's traveling this way. They collide, form a 50 gram ball of clay. We want to know the overall speed afterwards. So this would be the overall speed in the x direction squared plus the y direction squared. Okay? And then we want to know the angle that they head off on. So more about that in just a minute. So this one is completely just going in the horizontal direction. This one just makes it a little bit trickier because it has velocity in the x direction. Maybe I'll call this one I call this mass 20, so this is mass 30. Velocity 30 in the x direction, initial, and it's also got a part in the y direction. Just to keep the picture a little bit clear, maybe I'll put it over here. Velocity 30, y direction, initial. Okay. I should have just called that mass 2 and mass 1 or something, but we're stuck with 20 and 30 for the time being. Okay, so for the system, in terms of the y direction, maybe it's a little easier to do the y direction first of all, because this one doesn't have a y direction. We can figure out how much momentum we have in the system initially in the y direction, because the only one in the y direction that has momentum is this one. So this is 1 meter per second that way. We'll have to figure out how much of it is this way, right? This is the overall speed here. We need to figure out how much of it's in the y direction. I drew it over here, but it's the same thing. I could have drawn it over here. Okay, so this is 30 degrees. We'll have to do a little bit of trig here. So the sine of 30 is the side I'm looking for. Velocity 30, y initial, divided by this 1 meter per second. Right, that's the hypotenuse. So sine of 30 is a half. This turns out to be 0.5 meters per second. That's the velocity of the 30 gram in the y direction initially. And from the picture, you can see that it's negative. Okay. So the initial momentum of the system in the y direction is just made up of mass 30 times velocity 30 y initial, which is a negative number here. The final momentum of the system, initial final in the y direction, now they're stuck together, so you have mass 20 plus mass 30, and then speed in the y direction afterwards. Okay, so the initial momentum of the system in the y direction is just contained with a 30 gram mass. And you can figure that out. We have everything that we need here. This is before the collision, after the collision. This is again the y direction. They're stuck together, they have a common speed in the y direction. We'll have to do a similar thing for the x direction. This one here turns out to be velocity 30, just like we did over here, which was 1 meter per second, times the cosine of 30 degrees, right? So you get a little bit better picture going on. This is 1 meter per second. This was velocity 30 x initial. This one over here was velocity 30 y initial. And then this is theta. So the cosine side would be this. So the cosine of 30, that's the adjacent side, velocity 30 x initial divided by 1 meter per second. This turns out to be 0.866 meters per second. That's velocity 30 x initial. And then I know it's this way, so I've got to put the negative sign there. Okay, so first of all, use this to get velocity y after the collision. Now we're working on the x direction. The initial momentum in the x, well, this one has an x momentum, so this would be mass 20, and I just called it 2 meters per second, plus mass 30, and then you have to do velocity 30 x initial. Now the final momentum in the x direction of the system would be their combined mass 20 plus mass 30, and then Vx. Okay, so set this equal to this, right? Initial momentum, set it equal to final momentum. The only thing that you don't know is Vx, and then you can solve for that. Okay? And then again, the overall speed is what they're actually asking for. You'll have to do this. Now once you get Vx and Vy, let's see if we can kind of get an idea which way it's going to be going afterwards. Well, the 50 gram ball is definitely going to be moving down in the y direction. And in terms of the x direction, let's see. So this would be 20 times 2, which would be 40. This would be 30 times 0.866. If I can find my calculator. .25. So I think after the collision, maybe it looks like it's actually going to veer off down and to the right. You'll have to verify that. Anyway, here's what I think is happening afterwards. So to get theta, you can use the inverse tangent. Well, first of all, the tangent of theta is the y part divided by the x part, and then you can use the inverse tangent to get theta. Oops, there you go. X part, y part, I'm guessing that it's moving to the right and down. It could be it's moving to the left and down, but I think we're okay there. And then use the tangent of theta is y over x, and then the inverse tangent of y over x will give you theta. Okay, so that'll give you this theta. We'll have to see how they actually want it reported. Let's take a look back at the actual problem. Okay, so it says express your answer in degrees south of east. So the way that I think we set it up, where the x part is to the right, y part is down, that's the angle that we're actually measuring south of east. Okay, let's look at the next one. That's the most involved problem so far of the semester, just because it's really 2 problems. Okay, final problem. A firecracker in a coconut blows the coconut into three pieces. Two pieces fly off south and west, perpendicular to each other at 24. The third piece has twice the mass of the others. What is the speed of the third piece? Okay, so there's no momentum before this explosion. There can be no net momentum afterwards. Okay, so we'll have to take that into consideration, just like we did before with the Hunter and the recoil. The difference here is this is in 2 dimensions. It's just going to be more work, but it's the same exact idea. This might seem a little tricky because we know 2 equal masses, and then the other one has twice the mass, but we don't know how much the mass is. Let's just set up the problem, and maybe mass will cancel out. Okay, let's take a look at it. Okay, so we've got one mass flying off to the west, 24 meters per second, another mass flying off south, 24 meters per second, and then one that's twice as massive, so I called it 2m. It's got to fly off some different direction. So there's no momentum before the explosion. There can be no net momentum after the explosion. I mean, the individual pieces have momentum, but the system, there's no external force on the system, just an internal force. So this is going to fly off this direction, and it's going to have a part that way. So the momentum of the system afterwards this way has to be equal to the momentum of the system afterwards that way. Same thing with up, same thing with down. This is not speed, this is momentum. Momentum, momentum. Maybe I'll call this one left, right, momentum up, momentum down. So the momentum to the left would be m times 24 meters per second. This one doesn't have any horizontal momentum, so then this would have to be equal to 2m from this one, and I'll just call this Vx. Okay, the m's cancel out, so 12 meters per second. That makes sense, right? I mean, you've got 24 meters per second contained in one mass going that way. You'll have 12 meters per second contained in twice the mass going this way. And you could do the same thing up and down. So down you have, the only one is this one, m times 24 meters per second. This is 2m times Vy. So set those equal to each other, you'll see the same thing. Vy turns out to be 12. And then that makes sense too. M times 24 is the same thing as 2m times 12. And then this has to be 45 degrees, right, for that to happen. Okay, very good. Any questions, send me an email, and I'll talk